Hi everyone. In the previous videos we saw how we can do the backpropagation algorithm and how the network train and learn with different datasets. So now when we have calculated all the derivatives with respect to each weight and each bias, we will adjust the weights and bias to decrease the error. With these derivatives, we can have the Jordan matrix that will store them, and we will use it to decrease or increase the value of the weights. Because of the optimization problem we want to do is to decrease the error output, we will need to go in the opposite direction of the derivatives and of the weights and biases. So the idea is that I will call it the gradient, okay? So when we have calculated the gradient of every weight and bias, we will do the next thing. For each weight, okay, we will decrease it with the minus because it's in the opposite direction, because the optimization problem is to decrease. And now we will have a constant that will be the learning rate, and then here we will have the derivative of the error with respect to the weight we want to update. For the bias, it will be the same. We have a bias and we will have a learning rate for the bias, and we will, with the derivative of the error with respect to the bias, we will update every weight and bias. This constant will depend on how we want to go, how fast we want to go to the minimum. Okay, so imagine that we have here a 3D graph, okay, and we have here a surface, okay. The idea is that we want, this is our start point, and this is the gradient, okay, that is in this case the matrix with all the weights and bias. We will go in this direction to reach the minimum, okay, but this constant will reduce the length of this vector, okay. So this is very important because if we want to learn for every data element, we want to only learn a bit of each each data element. So if this is very large, we will have like very fluctuations, because we will go in this direction, then in this, and this won't help us to go to a reach minimum. Instead, if we do uh, um, little changes to the weights, we will go very slowly to the minimum, and we will be nearer to the minimum. So that is why it's very important to have a low learning rate. So in this case we will be using 0.001, for example, or 0.01. Then another thing that is very important, sometimes it is better to store all the gradients for a specific amount of data elements, and then with all of the gradients we sum up all of them, and then we adjust the weight. So this is called the mini-batch gradient descent. In this case, when we use only one data element to adjust the derivative, it's called SGD. But sometimes it's better to use mini batches. Okay, so how we will use it? We will use the same formula, but instead we will be summing all the derivatives of the data elements in the mini batch. So for example, if our mini batch is 20, we'll have 20 elements, okay, and we'll calculate the derivative of the error with respect to the weight as the sum from I equals to 1 to 20 of all the derivatives in that specific position. So in the I will put here I. So in the time I, in the millibatch I, we will calculate the gradient. And the same for the bias. So this is quite useful because it will help us to optimize the gradient descent. But also there are also a lot of techniques to improve the performance of the optimization of of the problem, and we will see some of them in the next videos.